Howdy! We're ready for Chapter 6. Chapter 6, Fundamental Chemistry 1. So this is a chapter on solutions. And it's really about concentrations and learning to deal with these. So it's a lot of math. So it says calculations in here, molarity, molality, percentage. The definitions are really just the formulas. Keep in mind, I will give you helpful equations. So you will have a sheet that looks like this that has helpful equations part 2. Alright, and it is the first half of that sheet has the equations that we'll be dealing with. So you don't have to memorize all of these. You'll have them, you can use them on the test. It's not very overly difficult because of that. The hardest part then is getting an idea of these concepts. So let's explore these a little bit more. So we're going to start with the basics for a solution. A solution is made up of two parts, the solvent and the solute. All right, and so the way I usually like to just kind of draw this out is then a solution as a solvent and the solute. Now the solvent is what you have more of. You've got more of it. The solvent dissolves. The solute is dissolved. If I spell dissolved, and so learning this language really kind of helps for this. When I was a young man, just starting to drink coffee, oh man, my dad likes strong coffee, and so I would always add a bunch of sugar to it, a bunch of things to it, and he would always tease me and say, "You want a little coffee with your sugar?" And he was actually right. If I'd added more sugar, then it becomes the solvent. Alright, so I might ask some questions as simple as if I have 5 milliliters of acetone and 3 milliliters of water, what is the solvent? And so the solvent is just whichever one I have the most of. Alright, so one thing that we want to be careful of here is that when we start mixing these, the volumes are not additive, and we'll see that happen over and over here where we add the grams or we do things with the volumes, but if you add two different liquids, you cannot predict what their volume will be because the spacings and their densities interact with each other, and so you can't just add up the volumes. All right. Now I also have on here that it says the aqueous solution, that the solvent is water. That's easy enough. But we can also have air, and it says the solution in nitrogen. And that's because 79% of air is nitrogen gas. And so you have all these other things that are in air, oxygen and water, carbon dioxide, carbon monoxide. And so they're all dissolved in the nitrogen because there's more of it. So the solvent would be N2. Okay, an alloy, which is just a mixture of metals. All right. Again, we've got our definitions for electrolytes and non-electrolytes. Not a problem. In lab, we run into students running trouble all the time between the difference between clear and colorless. So clear means you only see one state of matter. You don't see two different liquids where you can tell where one is and where the other one is. Oil and water, when they don't mix like that. Or if you have a solid floating in a liquid, then it would be cloudy. All right, so the opposite of clear is usually cloudy, and colorless is just lacking color. So you think solutions can be blue and clear, all right, or cloudy and yellow, those kind of things. So don't get them mixed up. The next thing the book goes into is the difference between suspensions and colloids, and so it's My real problem with that section is their numbers are off a little bit. They're a little bit dated. Um, so uh, there's a lot of work that goes into it. So suspension is when you have a bunch of tiny particles that aren't dissolved on the molecular level. And they're not, each molecule is not being surrounded by the, instead of being surrounded by the solvent, then instead you have a clump that's just eventually going to be settling out. Now, a colloid is when those particles are so small that they stay in, and just the natural differences in temperature and motions caused by the Earth are enough to keep it suspended. So if you've ever gotten antibiotic medicine and it was that pink medicine, and then they mix it and they say you have to shake it, and if you let it set, you can see it slowly settle out. That's suspension. It's not dissolved, it's just floating in. All right, so I won't do much of those other than maybe those definitions. All right, so then the next one up, how is solubility? And our term is light dissolves light. Now in solubility, we're now looking at this in slightly different terms than we did originally. Originally we looked at solubility and we're discussing it in terms of solubility was about how is something soluble or is it not. It's just a yes, no. Now we talk about how much. All right, and solubility causes us some interesting things. All right, so this idea that temperature increases solubility. I'm going to play with this idea on gas. We'll come back to in just a little bit. But I want to look at these definitions, saturated and supersaturated, and play with this idea of solubility. So if I take a beaker and I put some water in here, so here's my water, and I start adding some salt, some NaCl. Now, salt is soluble in water, so it dissolves and it dissociates and it spreads out. But what if I keep adding salt and keep adding salt and keep adding salt? Eventually, this solution gets as much as it can hold, and any extra comes out as a solid. So down here I have some NaCl that's a solid, and up here I have some NaCl that's aqueous. Aqueous, if I can make A. Try that all again. There we go. Aqueous. All right. So what's going on is actually more complicated than it seems. All right. What happens is you get local little places of higher temperature and little places where, as the water comes by, it grabs up and dissolves some of the sodium. It goes up into solution and splits up. But now I've got too much in solution, and it's got too much there, and so some of it has to come out. And so some's constantly going in, some's constantly going out. All right, so this is much like what we refer to as, this is called a dynamic equilibrium. Dynamic means we can change it. Equilibrium means the rate going in is equal to the rate going out. Now, rate is speed. All right. And so how fast things are going into solution is as fast as they are coming out. So if that's happening, the amount of salt here doesn't change, but the actual atoms that are involved are constantly being swapped at the surface. Some are going in and some are coming out, and they're constantly going back and forth. All right. Now we can, it's dynamic, we can change this. If we increase the temperature, we increase the solubility of salt in water. All right, and this gives us great power. So I can raise the temperature and more of this salt will go into solution than is coming out. And so we'll have less solid and more in solution. If I cool it down and lower the temperature, Then I lower the solubility and it comes out faster, and I'll end up with more solid down here and less in solution. Easy enough. So this idea of equilibrium will hit you with this term a lot. Rate in equals rate out. What I usually like to think of is going to the store. All right, and so when I go to the store, I'll pick on Walmart. Everybody likes to pick on them. So I go to the store, and there's people in these checkout lines, and what they want when you get there, you want to get out of the line right away. But you notice there might be 3 of these, and only one of them is open. And it drives you nuts every time, right? And so what they want is, as more people get in line, they get you out at that same speed. All right. And so if they have 4 people in line and a 5th one joins and they still haven't got it out, the line would get longer. So what do? They open up a second one so they can get them out faster. All right. Or what if, but they don't want everybody just zooming in and zooming out. They want you standing in line because you make a lot of purchases sitting there looking at the magazines. Ooh, I need a pack of gum. Or hey, there's some playing cards. Or they always have toys or candy there so that your kids will gripe and say, hey, Mama, I want that, I want that, I want that. All right. They want you buying all that and standing there for a little bit of time and not just immediately leaving. And so you'll notice that they can control how fast people go in and out by how many of these stations they open. And so if they ever close one, or I'm sorry, have them so many open where they're getting them out twice as fast as they get in, they'll get to where there's no line. And they'll immediately come and send this person on break so that they can slow everybody down and get the line to build back up. And that's how they can control how fast they get people out of the line, is by how many of these they have open. All right, and so it's a dynamic equilibrium. And it also comes into play what time of day. So if it's 5 p.m., everybody expects you're going to have to stand in line no matter where you go, and you might put up with a line of 5 or 6 people. You might grumble about it, but it's that way everywhere you go. And you go, oh man, why don't they open more? Well, they know that you're still going to continue shopping. They're still going to, so they make enough money by you buying that extra stuff and by the fact that they'll eventually get you out of there and they didn't have to open up and pay another employee to get you out faster. Okay. Now, if you go at 3 a.m., you might only be picking up a couple of things and you don't expect to stand in line that's 5 people deep. You might just say, forget it, and walk out. All right. So they actually lose money if that line is too long at that time. So they control this by how many stations they have open, and so that's what they have different expectations at different times for that. So dynamic equilibrium. Now we can play with this picture a little bit, and the key to it is temperature. So when I have as much dissolved as I can, it's saturated. So this solution will be saturated if I see any solid down here. So the solution is saturated. Now when I want to play with this a little bit, I can make a temporary condition super, in other words, more than saturated. All right, so supersaturated is a temporary condition. And this is the same idea as we use to make Jello. All right, it's the same process. A lot of times we use this as a recrystallization process. So here's the way you would do that. You would raise the temperature until it's hot enough to get everything dissolved. And once everything's dissolved, you slowly cool the temperature down. And if you cool it down gently enough, it'll stay in solution for a limited time. While it's in solution, that's a supersaturated solution. And if you let it cool slowly, it'll come out one molecule at a time, and usually it'll come out on, it needs a nucleation point, either another crystal or a scratch in the glass, or if you wanted to make rock candy, a piece of string or a popsicle stick. All right. So if I take some sugar and dissolve it into water and get as much as I can into that boiling water, and then let it cool down real slowly, it'll come out as one big crystal. It'll come out one molecule at a time, and it'll just form these large crystals. If I cool it down real fast, it'll come back out as a powdered sugar again, and it won't be super pure. It just comes out all at once, and anything else that was in the water comes out at the same time. All right. So when you make Jello, that's actually the instructions for Jello. When I look at that, it says take the box and dissolve it in so much hot boiling water. And then once you've got it, stir it completely until it dissolves. Add some cool water. You're just cooling it off gently, slowly. Then you're gonna put it in the fridge and gently cool it and let it slowly come out. And instead of forming a solid, it forms a gel and traps the water in there. All right. If you've ever tried to make Jello and speed up the process, stick it in the freezer. Ooh, it's nasty. It ends up tasting and looking about like the bottom layer of your shoe. Just don't do it. Don't do it. All right. So this idea of dynamic equilibrium, the rate going in is the rate coming out. We'll also ask about saturated and supersaturated. So people say, how can it be more than the max? Well, it's a temporary solution. It just happens for a small amount of time. All right. So we're ready for Henry's law. Henry's law, one of my favorite gas laws. It says the number of moles of gas dissolved in liquid at a given temperature is proportional to the partial pressure of the gas. Whoa, man, what does that mean? So this idea of pressure goes up, which can be partial pressure, which also means concentration. So if I have a mixture of gases, then the pressure of the individual gas. That means the solubility also goes up. This is important. This is why we give a patient oxygen gas. All right, and so this is also, you've seen this before. So if I show a Coke bottle or can here, what's going on then? And when I've got it closed, then it's under pressure, and I've got my CO2 is under pressure. If it's under pressure, it dissolves in the gas. Now this CO2 is dissolved in the gas. When I open it, I've increased the volume. That'll lower the pressure. Remember, Boyle's law, pressure and volume inversely proportional. So increase the volume, lower the pressure. So then that lowers the solubility. So that means the CO, that's when you get a bunch of bubbles come out, all that CO2. Now we want to keep in mind CO2 actually reacts with the water. And I'm going to use this funky looking arrow because it's an equilibrium, and it makes carbonic acid. And so when all the CO2 has left, we'll see that that means you can taste it. What you're tasting is the absence of carbonic acid. All right. And so when we say, oh, the Coke has gone flat, then it's because all the CO2 has come out of solution. All right, or enough of it is. This is the same process that your body knows to breathe with. And so we breathe to get rid of CO2, and our body monitors the carbonic acid. So you bringing in oxygen is kind of a side product. All right, and so if we were to give a patient too much oxygen, then they wouldn't have any CO2. And if we drive out all the CO2, they'll stop breathing on their own because they won't have that drive to breathe. So they have to have a little bit of CO2 built up to actually trigger their body to say, oh, I need to take a breath, get rid of the CO2. All right. So it's easier to monitor the buildup of CO2 than it is for our body to monitor the lack of oxygen. Okay. So this also is the reason why we have to worry about scuba divers. When you go scuba diving, so I'm gonna pick on let's pick on salt water. So if I'm doing salt water and I'm sitting here at the surface, and let's say I'm out in the ocean, so if I'm sitting here at the surface, I have 1 atmosphere of air pressure above me. All right, and then for salt water, if I go down 3 1/3 feet, all right, then that's another atmosphere of pressure. So if I go down 3 feet, I'm under 2 atmosphere. I've doubled the pressure. If I go on down 6 feet, I'm under 3 atmosphere. And so you can see you don't have to go very far down before you're down here swimming. Let's give us somebody is swimming. There he is, having a great time. Bubbles coming up. There we go. And so you're down here swimming, and you don't want to use pure oxygen in your tank because that leads pure oxygen, too much oxygen like that causes oxygen narcosis. Oh man, it's let's see. It's pleasant at first, and then you become psychopathic. So you'll start giggling and laughing and having a good time, and then you'll try to kill all your dive mates, and then you'll pass out. So not really good for being under the water, especially because everybody always carries a dive knife with them. So no, thank you. So what do we actually do then? We use compressed air, and so this compressed air is controlled by a regulator. And modern scuba diving owes a lot to this invention of the regulator. Jacques Cousteau invented the regulator. And what it does is it says, hey, if you're trying to breathe down here, and let's say you're under 20 atmospheres of pressure, your lungs aren't strong enough to pull in and to bring in that air. And so what the regulator does is your scuba tank's got real high pressure gas in it, and then there's a regulator on. It's a two-part, one on the back behind your head on the nozzle, and then one on the part that goes on your mouth. And so that regulator that goes on your mouth, so the one on the back lowers it a little bit, and then the one that's at your mouth, it has a membrane in it, and it matches the pressure from the water to the pressure of air it lets in. In other words, you breathe, even though you're way at the bottom under 20 atmospheres of pressure, you breathe as if you're at the surface under 1 atmosphere. So your body, you can breathe normal. Now, you're bringing in all this 20 atmospheres of pressure of gas into you. Most of that air that you're breathing in then is nitrogen, N2. Your body isn't doing anything with it, but it's under such high pressure, by Henry's law, it'll be soluble in your blood system. Then you start to come up. Well, as you come up, the pressure goes down and the solubility goes down. And if you get too much of that come out at once, then it'll come out as bubbles. You can only breathe so much of this out at once. Your body's only equipped to get rid of gases at a certain speed. So if you overcome that, you get bubbles, and that's called decompression sickness. It's also called the bends. They call it that because it's all those bubbles get stuck in your capillaries, and it's extremely painful. And you bend over and assume the fetal position, and it can be lethal. Matter of fact, there's only really one good cure for it and treatment for it, and that is to get you into a barometric pressure, right, chamber. And so if they can get you into a barometric chamber, raise the pressure, that increases the solubility, all those gases redissolve, and then slowly bring the pressure back down so that you have time to breathe off those extra gases. All right, so Henry's law, it's also the reason why we give a patient, if they're struggling to keep oxygen in their system, we give them increased oxygen flow, but we don't have to put the whole thing at pressure because it's based on Dalton's law of partial pressures. If we increase the concentration of oxygen, we're increasing the partial pressure. And so that makes it where we can get greater solubility in there. All right, so we're ready for these terms. So we've got all these different concentration terms, and the hard part for this chapter is you have to keep up with what is the solute, what is the solution, and what is the solvent. So when they give you a problem, you're going to have to identify these parts, and then you have to make sure they're in the right units and plug them in. All right, so when we're doing these equations, I give you these. You don't have to memorize them. The first one up is percent mass over volume, percent M over V. All right, so it says take the grams of solute over milliliters of solution. And then times 100. Anything with percent, it's got this times 100. All right. So that one, a lot of times, is called percent by volume. And that's an unfortunate name because, remember, volumes are not additive. So we never take milliliters of solute over milliliters of solution. We just can't do that. All right. It's not going to be reproducible. This grams over milliliters is used a lot. You have to be careful. Don't get it confused with, for instance, density. So the density would be the grams of solution over milliliters of solution. And there'd be no times 100 because it's not percent. So be careful. They're not the same. So grams of solute over milliliters total solution. Most everything has on the bottom the total solution. All right. Now, don't get this confused with percent by mass, or maybe they write it percent mass over mass. Both of these are equal. They're the same thing, and it's the grams of solute, what we're interested in, over the total grams of solution, and then times 100. So, whoop, off the screen, but times 100 because it says percent. All right. Now that one's easy enough. We use that a lot, but that percent mass over mass might not be scary enough. So grams of solute, grams of solution, times 100 may not be scary enough. The percents might be really small, and so we use that one a lot when we're talking about maybe just normal concentrations or the amount of sugar that's in our food or something like that. But what if it's something that even a very small amount is dangerous? All right. So then we use this idea of PPT. Now PPT is part per thousand. Part per thousand. In other words, x over 1,000. Well, remember that percent is x over 100. So it's the same idea as the percent. So PPT, we'll take grams of solute over grams of solution, and then we'll multiply it by 1,000 instead of by 100. And this gives us a little more scary number. And so if you saw something that said 0.0000001%, you'd be like, oh man, that's really low. I don't care. But it might be a dangerous amount. So we need a way of communicating this. Now, food, PPT works great. But drinking water, a lot of times, we want, for instance, in Arkansas, we really worry about mercury in our drinking water. We want to have even lower concentrations. So ppm would be grams of solution over, backwards, grams of solute. What we're interested over grams of solution, the total, times m being a million, 10 to the 6. All right, so now we're instead of multiplying by 100, we're multiplying 10 to the 6. It makes it look a lot scarier. So then we have even ppb, part per billion. All right, it's x over a billion. So if I had said something was 0.01% or 0.5 ppt or 20 ppm or 300 ppb, and I asked you which one was more concentrated, you might struggle with it because they're different units. You've got to get them in the same unit. So instead, what I'm going to do is put them, this is percent, so it's 0.01 over 100. And PPT would be 0.5 over 1,000. ppm would be 20 over a million, 10 to the 6, right? And this would be 300 over 10 to the 9th, which is billion. And I'm going to type it all in my calculator and figure out which one's the biggest. So let's see, this would be 1 times 10 to the minus 5th. This would be 5 times 10 to the minus 4th. This would be 2 times 10 to the minus 5th. This would be 3 times 10 to the minus 7. Remember this negative exponents? The smaller that negative is, the bigger the number is. So this one's actually my winner. This is the biggest, highest concentration. All right. So gotta be careful on these. They can be confusing. So there's two types of questions. One where they ask you this concept question, which one's bigger. But most commonly, they'll just give you how many grams of solution, and then you have to figure out how many. You'll have to figure out then what the ppm or ppb is. So these equations, they're all very similar, so they're not that difficult. All right. The one we use most commonly is this idea of molarity. So this capital M is moles over liters. Now, specifically, it's moles of solute over liters solution. That one we use all the time. We've used that in lab all the time. We might see something like this. And so anytime you see that capital M, moles over liters, we use molarity by far the greatest amount. Now, it's real common for us to give you a number in grams, and you have to find the molar mass to get the number of moles. So moles of solute over liters solution. Then we've got this idea of molality. And the problem with molality, we ran out of abbreviations, all right? So capital M is moles over liters. Remember, just moles is MOL, right? So all we could do drop was the E. There's no good abbreviation for molecule. A little m is meters, okay? So molality, they try to use italics M, but good luck writing that. So here's my capital M, my lowercase m. What am I doing? Italics M? I don't know. Good luck with that. But molality is weird because of it's moles of solute, but the bottom part is kilograms of solvent. That's the weird part. Alright? Now notice molarity and molality, neither one's multiplied by 100. Alright? But this kilograms of solvent, that means they're measuring this differently. And why is this useful? Well, if I'm doing this on a large scale, where I have a really big container, like maybe the size of the room you're in, and let's draw my guy up here, and he's got a bucket, and he's going to throw that bucket in and dump in the solute, and then he needs to dump in the solvent. Now if he's got a big 55-gallon drum, he can measure how many the mass of the drum with the solvent in it, dump some out, put it back down, measure it, see how much he took out, and so he can really quickly measure how much he added down here. And then maybe this stirs, the reaction takes place, and then they pump it out through some pipes or something. All right. So if we're doing large-scale stuff like this, the molality really comes in handy. Moles over kilograms. So that one is different than the others. All the rest of them have on the bottom liters or grams or milliliters of solution. All right. Now, one of the things that they hit you with in lab a lot of times is you have to be careful that the grams of solution is the grams of the solute plus the grams of the solvent. It has both. All right. So terrible. All right. So you always have to be careful. Are they giving you the solute? Are they giving you the solvent? Or are they giving you the total solution? So you're looking for dissolved, dissolved in. Those are your kind of keywords there. All right, so we're ready for this idea of dilutions. Now, it's unfortunate that we use this word dilution because if we make something more concentrated, it's the same math, it's just with different word for it, right? So a dilution, let's start with a container here, and let's say I have 0.2 moles of salt dissolved in this water, and I dump it into this big container. I won't even fill it up. It'll be way down here, right? So I dump it in here. How much salt is down here? Well, it's still that 0.2 moles. I didn't add any more salt. And then if I add a bunch more water and fill up this big container, as long as I don't add more salt, I still have the same salt. Now it'll be a new concentration. The moles that I started with will be equal to the moles that I end with. And that's the key to dilutions. And so we write M1V1 equals M2V2, really helpful equation for dilutions. Anytime you see diluted, we use this equation. But this is molarity, moles over liters. This is volume. Usually we use liters, or you can use both sides milliliters, it'll be fine. Well, what happens when I multiply these liters? I get moles equals moles. The moles we started with is equal to the moles we end with. These problems are nice and easy. We'll give you 3 out of the 4 variables. You solve the 4th. Man, super easy. They're great. Love those. M1, V1 equals M2, V2. Give me 100 of those on a problem. I'm testing. Take them all day. All right. Next thing we've got up is this idea of colligative properties. Colligative properties are neat because what's special about them is it only matters how much is dissolved, not what's dissolved. All right, so we just want to know how many particles are in here. So I've got a couple of different ones. I've got so normally we look at things. We look at the boiling point, so boiling point, and the melting point. And interesting thing happens. The boiling point goes up, and the melting point goes down. Now, vapor pressure is related to the boiling point. It's the pressure above a gas. It also goes up, all right? And so those two are kind of related. And so let's play with the boiling point. Let's figure out what we mean by vapor pressure and boiling point. So this is the effects we're going to be seeing. So let's look at, let's make a beaker here containing some water. So I've got these molecules of water, and as I warm this up, the molecules of water, they're bouncing around, and occasionally one gets up enough speed to overcome all the attractive forces between it and the other molecules of water around it, and it leaves out into the gas phase. All right, and so constantly getting these up, and that's called the vapor pressure. Right? Now that vapor pressure, if I raise the temperature, then I raise the distribution, the average kinetic energy of each molecule, and so more of them are likely to make it into the gas phase, and so we would raise this pressure. Now, at every temperature, I have a little bit of vapor pressure. Right? This is why we get evaporation. Is that the wind comes by, it moves some of that water, and so then it tries to replace it, and there's more space for that vapor pressure. Vapor pressure of water in particular is only dependent on temperature. So raise the temperature, it goes up, lower it, it goes down. See how easy that is? All right, now what if I take a similar thing, but now I've got some particles dissolved in it. Now I have, I don't know, some sodium in there or some chlorine. It doesn't matter what it is. Some of this water can make it up and go into the gas phase. Some of it will hit and bounce off. And if it bounces off, it lowers the vapor pressure. All right. And so as I lower that pressure, then I have to raise the temperature to get it up to even higher. Now, a special thing happens when the vapor pressure equals atmospheric pressure. You know, the pressure above here, or out here outside this container, when those are equal, that's the boiling point. That means if we want something to boil faster, we can lower the atmospheric pressure around it. We can use it in a vacuum, and it'll boil faster. Or we can use a pressure cooker. If you close this container off and you build up pressure up there, then the liquid has to get to a higher temperature before it can boil. That means it's going to be hotter. If it's hot, it'll cook the food faster. So that's the idea behind a pressure cooker. Right? So we could raise this temperature by either raise the boiling point by either increasing the pressure, or we can add some solute in it. You've probably added some salt to your water. Let's say you're going to cook some spaghetti or something, and you want to boil some water, and you want it to cook pretty fast, and so you add some salt to your water, and it gets the water actually hotter before it boils. And that means when you throw in your food, it cooks faster because the water is at a higher temperature. All right. Okay. Now there's a limit to that, but for food, because you add too much salt, and then everything tastes too salty, and nobody's going to want to eat it. So that's why we have pressure cookers. All right. This idea of melting point, the same kind of idea. So when things decide to start freezing, what happens is the molecules are going to get lined up in a very orderly fashion, and they form crystals. But if I've got these particles in here, you can see that it's tougher for these things to get lined up. They have to kind of push everything out of the way. And so what happens, why do we use this, is we can throw, if I go outside and I've got ice all over my my porch, and I go, oh man, I can't go outside, it's too slippery. Oh, gotta stay home, cancel, can't make it to work today, sorry. But oh no, I got someplace I actually want to go. I'm gonna throw some salt out there. Now the salt doesn't actually heat up the concrete. It doesn't melt the ice that way. The way it melts is it dissolves on the surface, and so that the top layer will have some salt dissolved in it, and we lower the melting point. Let's say it is 30 degrees Fahrenheit outside. So it's lower than the boiling point, I mean the melting point of my 32 for ice. Alright? But if I lower the melting point by adding some salt below whatever temperature it is outside, then it'll melt. Alright? It's warm enough to melt. So you add that ice, it depresses that melting point, and it causes everything to melt. There's a limit to how far down we can depress it, and the reason we use salt on our roads, especially, is because don't forget, salt splits. When we mix that in water, it dissociates, and so we actually get this 2-for-1. We get 2 particles for each formula unit of salt. Alright, so that's why we like to use salt on our roads. So we add it out onto the roads, causes everything to melt. Now, why is it a problem? Well, it gets down in the cracks, and then as the water evaporates, it leaves behind the salt, and it forms the crystals, and it spreads out any cracks that were in the road, causing potholes and the road to crack. Salt flows off to the side of the road as it melts. It gets down into the soil, kills off all the grass and the flowers, and so it's just not not a good situation. And then you might have been told never buy a used car from up north, right? And the reason for that is all the salt that they use in the winter that gets up under their car, and then the salt is an electrolyte, and so it leads to rusting. So rusting takes you have to have an electrolyte solution. So if you hit your car with deionized water with no ions in it, it's not gonna rust. But if you hit it with the salt water, it rusts pretty quickly. All right. Now we this is colligative property. It doesn't have to be salt. Now, what's nice is it's got this 2-for-1, but what if we had something that was cheap? All right, it has to be pretty cheap because we're going to use a lot of it. We use a lot of salt every year just for our roads. Um, it would be nice if it didn't dissociate and make an electrolyte solution. So uh, let's make something that's not going to be ionic then, so it won't be an electrolyte. Let's make something then that won't kill the grass. And so they found a compound, and the compound that they chose to test was urea. Now urea is nice; it's a covalent compound. It's a fertilizer for grass. It doesn't cause the cars to rust. Um, it worked great, and you get it. You go up to any farm, and if you bring your own bucket, they'll let you have as much urea as you can carry. All right. Now, where's urea found? Well, it's found in urine, and this worked wonderful. They tested it on the roads. It didn't cause all the damage to the roads, didn't cause damage to the cars. And in spring, you never saw such pretty flowers on the side of these roads. They were great. Uh, so they tried it a couple of years, and then they quit doing it. And the reason they quit doing it really came down to um, nobody wanted to drive down the P road. You roll the window down and you get out, something smells, and it was really just the smell. All right, and so they're still looking for other alternatives, um, and so we're still using salt. We occasionally put sand down, and it's more for traction. It doesn't dissolve, so it isn't going to be a colligative property. It's just going to give us a little more traction. All right, but to actually melt everything, we need it to dissolve, and so salt is really powerful. So let's look at our other ideas. Here we've got osmotic pressure, the pressure across the membrane. So most of you have studied osmosis. I'm gonna leave you to look at that. One thing real common there is it looks just like the ideal gas law. Let me show that real quick. So osmotic pressure. Oh, look at this. This is capital P. That's osmotic pressure, just as so capital Pi. So do it just as if you find this, but you got to dissociate all the ions. All right. So when you do N, it's got to be all the ions. Let's see. The last thing we have is this idea of equivalence. Now, equivalence, you're going to take the charge times the molarity. And that'll give you equivalence per liter. All right. So if I have 3 molar NaCl, I have to be careful because I need to dissociate. So that's 3 molar Na and 3 molar Cl. And so when we do this, you're just taking the magnitude of the charge. And so this would be 6 equivalents per liter. All right. So you have to be careful. So usually we'll ask you stuff like, I've got 2 moles per liter of, let's do calcium plus 2. All right, and so that would be 2 times the plus 2. That would be 4 equivalents per liter. All right, so that comes into play when we're doing a lot of our osmosis, and we use equivalents on a couple of problems in the book, but really what I care about there is just doing this calculation. So when you're doing these, you're really looking for the terms dissolved in or is dissolved in. You've got to identify what's the what's the solution, and what's the solvent. Okay? So once you're able to do those, this chapter's not too bad. So we'll catch you on the next one. Maybe we'll work a few practice problems of this if students start to struggle with it. But try some. As long as you identify that, it shouldn't be too much trouble.